So I'm James, and I'm going to tell you a story about activity analysis. So what's the problem I'm trying to solve? The problem is, suppose that there's some 250 something odd channels in some location, and some are full, maybe some are empty, and I'm driving by in my spectrum measuring van, and I'm going to try to measure what's available. Now, because I'm moving, I only get maybe 1,000 measurements, some numbers, to give me some perspective. And I can only measure one channel at a time as I'm going through my set of 1,000 measurements. So how do I find the good ones? And maybe can I also find some of the bad ones and use that as sort of a warning for people who are going to come behind me and actually use this data? So turns out that the answer to this question is hidden in the assumption of the activity being a simple Bernoulli random variable. If I assume that the activity of a single channel is a Bernoulli random variable, then the variance looks like this. And what's going on here? Well, you'll notice that there's a maximum that occurs right in the middle, and that all the low variance of this random variable occurs at the ends. It's sort of pushing out to the edges. And so what I'd really like to do is I'd like to pay attention to channels that have parameters that are on the edges, because those channels are going to require fewer samples to figure out whether they are occupied or not. So why is that true? Well, there's a couple ways to get at that answer, but the quickest and easiest is to consider a naive estimator. If you consider a naive estimator, you can do a little algebra and figure out that the naive estimator's variance is directly tied to the variance of the actual random variable. So that's a whole lot of equation and a whole lot of words, but what it really means is that at the tail end, what I really want to see is consistent samples from a channel. If the sample channel that comes out consistent, then that's actually really good. That's telling me that there's low variance. And I'll have to build a system around that idea to sift out channels that are useful. So in order to get an idea of why I'm going to take the approach I'm going to take, let's take a look at an analogy for tossing coins. So suppose I have a bag of coins, and they're not all fair. And so I want to figure out what the parameter of each of these coins is. So because this is the model, I'm only allowed to have maybe ELF coin flips. And now I need to ask a few questions. Well, given this number of coin flips, how should I distribute these flips? And when should I stop flipping an individual coin? How do I know when a coin is done? And if I have a low rate of, if I have a low amount of, excuse me, samples to coins, then how many coins can I actually get through? Turns out that this problem is actually pretty hard and kind of a pain in the butt to solve. So maybe I'm going to take a simpler approach. Instead of trying to actually figure out exactly what the parameter is, I'm going to try to classify. That is, I'm going to make 3 bins. I'm going to have the mostly heads bin, the mostly tails bin, and the somewhere in the middle bin. And in the mostly heads bin, I'll put all the coins that end up come with heads most of the time, and same for all the other bins. So the question becomes, well, what does this do to my strategy? Turns out it actually does a whole lot. What ends up happening is that I stop dealing with simple hypotheses. I stop figuring out how to deal with simple things that have fixed values, and instead I have to move to composite hypotheses. That is, I have to deal with things that are above or below some fixed threshold. Now, my hypothesis is going to end up looking like something in the middle there. So, no discussion of hypothesis testing is complete without a mention of Neyman Pearson. So, here's my mention of Neyman Pearson. The big thing I need from the language of Neyman Pearson is this definition of type 1 and type 2 errors. Those are going to basically end up being my performance metrics. And you can talk about it from like the missile detection problem. We can talk about whether or not we've got false alarms or misses or any of that other stuff. But I'll give some sort of a heuristic answer that tells you more what it actually means in this scenario. So the likelihood ratio, seen up at the top there, named Lambda, is basically the thing that I'm going to use to figure out whether or not one of these 2 hypotheses is true. And I'll make a decision based on whether or not that likelihood ratio goes above or below eta, the chosen parameter. Now, So there's a way to formulate this test so that it can actually be used to figure out composite hypothesis instead of the simple stuff that I have written here. But no matter what formulation I choose, these tests, which are sort of the de facto standard answer for, hey, I need to figure out a composite hypothesis, these tests have a big problem. And that big problem is up in bold at the top. They assume fixed sample size. That is not going to work out well with me trying to figure out how to get through as many channels as I can. So since I've now sort of said, well, my goal is to classify, my goal is to find useful things, maybe unuseful things, and sort of bin stuff into mediums, lows, and highs, this is the approach that I'm going to take. It's going to be basically a two-stage strategy. The two stages are, I'm going to first try to figure out how to build a classifier that has the smallest number of samples, or rather that can classify in the smallest number of samples. And then once I have a classifier that does that really well, I figure out how to distribute my measurements across the set of channels, and I'm done. Okay, so turns out in 1940-something, Abraham Wald actually solved this problem. And he introduced a thing called the SPRT, or the sequential probability ratio test. It's defined like this, and Wald basically makes the argument that if you use this test, you get a bound on the error. So how do I actually use this test? Well, if I define my sufficient statistic to be that thing up at the top there, this D, and I do a little algebra on that equation from before, I get this giant ugly mess here. Now, while this is hideous to look at, there's one key fact that I want you to keep in mind. Notice that the slopes, the thing in front of the thing in the back of the m's, is exactly the same in both equations. These are parallel lines. It looks like this. And this is the picture to keep in mind. And what's happening here is I've got this random walk that's trapped between these two parallel lines. As that random walk crosses the upper threshold, I declare it 0, and same thing for the, or I declare H1 rather, for the upper threshold line. If it crosses the lower threshold line, I declare H0. Okay, so that faint spot that you probably can't see over there is where it crosses the line. That's my stopping time. So in order to tune one of these guys, I have to deal with two fundamental curves. The first fundamental curve is the operator characteristic curve. Now, the operator characteristic curve has a fairly complex definition, but the graph is pretty simple to understand. And what does the graph tell me? The graph tells me how I declare a hypothesis based on what the parameter actually is. So, for instance, if the parameter is sort of on the edge below 0.25, I'm going to declare H0. And if the parameter is on the other side, I'm going to declare H1. Somewhere in the middle, wrapped around the threshold itself, the actual T that we're trying to figure out, is a region that I call the indifference region. And what's the indifference region? It's the region where I'm indifferent to making a mistake. So if the parameter was 0.3, and I said it was above 0.3, even though the parameter was actually 0.29, that isn't really a big mistake. On the other hand, if the parameter was 0.4, and I said it was below 0.3, that's a pretty big mistake. So over there, on that side of the curve, you'll see that it's really low because I want to have a very low probability of declaring that it's below the threshold when I'm on that side. Okay. But the thing that I'm really interested in is expected stopping time. This is the thing that I'm trying to control. I want to get this down as small as possible. You'll notice that the maximum occurs right at the threshold. Why? Because when I'm at the threshold, I'm stuck in the middle, I'm stuck in this indifference region, and I'm trying to figure out my way, and in order to get somewhere through that, those two sets of threshold lines, I've got to take more samples to wiggle my way out. So, that, the answer to that hypothesis test splits the interval into two regions. The stuff above my threshold and the stuff below my threshold. But I said I wanted to split the interval into three regions. So how do I do that? Well, I use two tests. I can use two tests, and I'll get two thresholds, and then I can chop the region up into a low, a medium, and a high. Now there's some sort of a combining rule, and it's pretty ugly to see in equations, but it looks really great in a graph. So there's the graph. So I've got two threshold lines, or four sets of threshold lines, and a random walk that's trapped between all of them initially. And as that random walk starts to fiddle around, it can walk down, it can walk up, or it can walk somewhere in the middle. Each of these different spots that it walks out of those two threshold lines gives me a decision. So if I cross the one all the way at the top, the solid blue line, that's the high region. If I cross the dashed red line, that's the low region. And if I'm somewhere in the middle, then I get an answer that's somewhere in the middle. Okay, so the stopping time for the 2 tests is actually bounded above by the stopping time for 1 test. So you look at this graph and you see that it's a mirror image of the expected stopping time that we started with before. Okay, so now Wald has given us the answer for minimum samples. Now I need to come up with a strategy for distributing these samples. So my strategy, greedy allocation. It's really simple to do, and it actually works out pretty well. So from that variance intuition, I figured out that what is really important is getting really close to those threshold lines. The further I am from those threshold lines, the further I am from making a decision. So the first thing I want to do is reward, or I guess in this case, discount proximity to those threshold lines. The closer I am to those threshold lines, the better my picture is, and the closer I am to making a decision. So with that in mind, the first term in my cost is the distance to any one of the outer threshold lines. The outer threshold lines are important because, again, I want to deal with those regions on the edges, and I don't want to deal with stuff in the middle. So if it's in the middle, that's bad for me. Now, if I just gave you just the distance to the threshold lines, nothing stops you from running away with measurements, or if I stop somewhere in the middle, some channels may end up looking better than they actually are just because they got lucky. In order to make that fair, or prevent you from getting lucky, what I do is I put a measurement penalty. The measurement penalty essentially imposes fairness. What the measurement penalty does is it sort of controls the amount of struggle between channels. Now, that's really difficult to understand in concept, but really easy to see in a graph. So here's the graph. And what you see in this graph is the cost among 5 channels when the value of lambda is low. Now you'll notice that the guys on the edges, the green one and the blue one, and even the black one, they sort of start dropping their cost really soon. And whenever I complete a channel, my cost goes to infinity, so I don't go back to that channel. I'm done with it. Now, the guys who are low variance, they run away with the measurements, and the guys who are high variance spend the rest of their time duking it out to try to get some measurements from each other, but they're all high variance anyway, so really I don't care about them. On the other hand, if I made the lambda high, constant infighting. Sort of a giant mess. I don't get the filtering process that I want. I don't get these guys to separate out the way I'd like them to. So I advocate low lambda. It seems to work out better. So, oh, I actually have 6 minutes. Awesome. So, a little bit about the performance. I sort of built this this idea of trying to figure out what the scaling is like, because that measurement regime sort of tends to become a problem. Sometimes when I've got low measurements, I'm actually in serious, I actually end up doing better than when I have high measurements. What does that mean? Well, take a look at these metrics for 1,000 measurements and some increasing number of channels. So the number that I figure out at the deadline, that's the first column. The number of samples that's required to get to 4 good channels, that's the second column. And the number of samples required to figure out everything, that's the third column. So this is kind of hard to make sense out of in tabulated form. There, at the bottom, there's the explanation of priorities, which is really the big thing. That's how I prioritize stuff. But this is what I really want you to see. As the number of channels goes up, my searches, the stuff that I figure out after, as the search space is increasing, that sort of bottles up, that sort of tops off. I reach some sort of maximum. And the reason is because I'm only given 1,000 measurements. There's actually a deep, profound reason as to why that's actually true, and it sort of has to do with one of the assumptions I made, but I'll give you a reason why that's true later on. It's sort of tied to the reason why this graph looks like this. What happens here is, as the search space starts to grow, as the number of channels I'm trying to sift through is getting bigger and bigger, the amount of samples I need to get 4 good channels. That is, I'm in a really hurry, and I really need 4 good channels right now, and I don't care what you have to do to get them to me. Get me 4 good channels. How many samples is that going to take? That value levels off. And it levels off at a pretty low number, much, much lower than my deadline, which is kind of nice, but unexpected. So, in order to figure out error performance, which is the thing that we always talk about when we're talking about a hypothesis test, I need to build some sort of an estimator. So thinking back to that naive estimator, or, well, I need a classifier to compare against. Thinking back to that naive estimator that we had at the beginning, I can actually use that naive estimator to classify. I take all the measurements I possibly got, split them up amongst all the channels, distribute them evenly, and then use that p-hat estimator to actually bin my channels. Now I'll make 2 types of error. They're my alphas and betas from the name and Pearson language. And what those errors are, and this is sort of a little bit hand-wavy, what those errors are actually missed spectral opportunities and chances of running into things. Now that's not exactly right because I'm using both sides, but you can sort of think of it that way, and it sort of gives you an idea of what it is that's going to happen with this next graph. So in the next graph, this is the probability that I tell you the wrong thing. I say something is empty, but it's actually not. And you'll notice that our method does a heck of a lot better, 1 order of magnitude, when the number of channels is high. There's a great reason for that, and we'll see why in a minute. In much the same way, this is the probability that I didn't use something that I could have, and again, we're doing a lot better. So, why are we doing so much better? Well, it turns out there's a little devil in the detail. And that devil in the detail is that I assumed that the parameters were coming from the uniform distribution. Now, because I've got a uniform distribution, as the pool of channels that I'm searching through grows, so does the pool of good channels. And because that pool of good channels is growing, and my system is tuned to aggressively look for good channels, there's more stuff to find, and I find it sooner. Now, when we were looking at that operator curve, the probability of making an error is directly tied to how far I am from the threshold. As this pool grows, stuff that's far away from the threshold is much further, is much more available, much easier to find, and I can get through it much quicker. And so I fill up that good bin a lot faster. And it also turns out that the test is slightly biased to the left side than the right, but the reason for that is sort of hard to explain. So, moving forward, maybe that meta distribution might not be true. Maybe I'll get in trouble. And maybe the set of good channels isn't that big. And if it is, what ends up happening is that I basically degrade to that naive estimator. I end up having to blindly scan because there's nothing good for me to find. So I could possibly consider tuning the test for different meta distributions, maybe pulling those thresholds back in case that set is smaller or larger. I could try to figure out what the computational complexity is. It turns out that when the number of channels is low and the number of measurements is high, it's a waste of time to do what I did because it's very complicated and it doesn't get you much better performance. On the other hand, when the number of channels is high and the number of measurements per channel is very low, we end up doing a heck of a lot better because we won't tell you about everything, but what we do tell you about is worth gold. That's the basic idea. Questions?